We now come to June 07 paper 1 question 4, similar sort of question to the previous question in terms of resistors being connected in series. If we look at the diagram, we can see X and Y, so far we don't know any resistances. We're given voltages, and hopefully either we'll be given currents in order to work out resistances or resistances to work out currents. But in the circuit below, the reading on the voltmeter is 3 volts, so we have a 3 volt here. The battery provides a voltage of 3 volts. The reading on the voltmeter, is 2.4 volts. So this voltmeter here is reading 2.4 volts. Now, straight away before going on, I know that the voltage across Y must be equal to 0.6 volts. And that's because we have 3 volts total, 2.4 volts plus 0.6 volts. So what is the voltage across the resistor Y? Well, we can say 3 volts is equal to 2.4 volts plus the voltage across Y. Therefore, the voltage across Y is equal to 3 minus 2.4, which is equal to 0.6. So 0.6 volts. Quite a lot of marks, 3 marks there for a very simple calculation. The current through X is 0.2, so we have a current going through here of 0.2. What is the resistance of X? Alright, so we have 0.2 amps going through here. What is the resistance? Well, we use the equation V equals IR to work out our resistance. That means that V, the voltage across X, is 2.4. So 2.4 is equal to 0.2 times R. So R is equal to 2.4 divided by 0.2, which is equal to 12. So we have a 12 ohm resistor connected at X. Why is the current, the next part of the question asks, why is the current flowing in resistor X equal to the current flowing in resistor Y? Well, if we look at these, resistor X and Y are connected in series because, and that means that the current will flow. So the answer to this is that both resistors are connected in series. And so the same current flows through both. In a similar question to the previous one then, we now have a resistor added in parallel. This time the resistor is added in parallel across both, but we're given the current flowing through here rather than the voltages. Alright. The current through Z is 0.3 amps and the current through X and Y is unchanged. So we still have the same current going through there, which means that for X and Y, if there's no change here, that means that X must be the same PD across it and Y must be the same PD across it. But we're asked, what is the new current supplied by the battery? Alright, if we have a current coming out of the battery here, the current comes around and stays constant until it gets to here. 0.2 amps going down this arm and 0.3 amps going down here. That means that the total current that comes in there must be equal to 0.5 amps. Because when it gets to this point here, it splits, 0.2 goes there, 0.3 goes there. So again, what I would say is that I is equal to 0.2 plus 0.3, which is equal to 0.5. So the current is equal to 0.5 amps. What is the voltage across the resistor Z? Well, resistor Z is connected in parallel with X and Y, and it's connected back to both ends of the battery. If we trace back from this side, we come back to here. If we trace back from here, we come back to this side of the battery. So Z will also have 3 volts. And there's no calculation to show there. That should just be fairly obvious that we have 3 volts across Z, because that has 3 volts and this is 3 volts. Calculate the values of resistance Y and Z. Well, we know that Y has got a voltage of 0.6 across it. That was from the previous question. So we know this is 0.6 and we know this is 2.4 volts and 0.6 volts. We know that this has got 3 volts. So for Y we've got 0.6 and we've got a current through it of 0.2 amps. So that means that we can say 0.6 is equal to 0.2 times R So R then is equal to 0.6 over 0.2, and that gives us R equal to 3. So the resistance of Y is 3 ohms. Z, the resistance of Z. Well, to find the resistance of Z, we're going to say again, it has 3 volts across it, and it has a current of 0.3 amps. Therefore, the resistance of Z is going to be equal to 3 divided by 0.3, which is equal to 10. So it is a resistance of 10 ohms. Next question is the combined resistance of X, Y, and Z. So we now have 3 resistors, and I'll just draw those resistors here. Resistor X we had already calculated to be 12 ohms. Resistor Y we've calculated to be 3 ohms, and resistor Z we've calculated to be 10. So the first part of this, I've got these 2 resistors in series, so that's 15 and 10 effectively. And now I can use the formula for resistors in parallel. So we have 2 resistors in parallel, therefore our total is equal to the product over the sum, so that's 10 plus 15 over 10 times 15, and that gives us then 150 divided by 25, which is 150 divided by 25 gives an answer of 6, so it's equal to 6 ohms. Now a quick check, whenever you're doing these types of calculation, the total resistance should be less than any of the individual resistors. So the smallest individual resistor there is 10, 6 is less than 10, so it looks as if we might be in the right kind of area with regard to that. We then come to another static electricity. Thunderstorm clouds contain many millions of water droplets and ice particles suspended in air. Collisions between the water droplets and ice particles create a positive charge at the top and negative charge in the lower part of the cloud. Explain in terms of electrons how the top of the cloud gains a positive charge and a base of the cloud a negative charge. Now this is very similar to the previous question that we had about how things become positively charged and negatively charged. So at the top of the cloud, so the top of the cloud loses electrons. Because it loses electrons, it then becomes positively charged. And the bottom of the cloud gains electrons, and it becomes negatively charged. So there's a movement of electrons from the top to the bottom, and in order to get that positive or negative charge explanation, you could maybe write a few more lines in there about that, but that's essentially what happens. The top of the cloud has lost electrons, they move to the bottom of the cloud gains electrons, so the top becomes positive.